Hi, I'm Aryan Chaudhary. This is my Physics Lab 3 on black holes. So, the table of contents. In this lab, I'll be covering 5 main things: the introduction, first computation model to find the mass of the black hole, the second computation model to find the escape velocity, the conclusion, and finally the error analysis. So, the objective for the part 1 is to find the mass of the black hole using the model, which will be modeling the orbit and the gravitational interaction between the black hole and the star. Then for the part 2, I'll use the value of the mass of the black hole from part 1 to find the escape velocity of a spaceship such that it escapes the gravitational influence of both the planet and the black hole. So some of the key ideas in this experiment are Newton's second law, which is the rate of change of momentum is proportional to the net force on the system, the gravitational force, which is the force of gravity, the perpendicular and the parallel forces of net force. And since this is just a coding lab work, there would be no actual real life experiments. So the system for part 1 is the star, and the surrounding is the black hole. And for part 2, the system is the ship, and the surroundings are the black hole and the planet. So the preview of the results. So from my experiment for the part 1, I found the mass of the black hole to be 8.82 into 10 to the power 33 kilograms. And for part 2, the escape velocity came out to be this. So the computation model for for the code, I would be using the gravitational force formula, which is as follows: minus gm, capital M upon magnitude of r square into r hat. Here the small m is the mass of the system, the capital M is the mass of the source, r is the position of the system minus position of source, and r hat is the direction vector. Now, for this, there are two components of net force in a circular motion. First is the parallel component, which changes the speed. This is parallel to the direction of motion. The perpendicular component, which is perpendicular to the direction of motion, and it changes the direction of the system. So we can see the formula for both. And then code for part 1. So the initial conditions are as follows. I inputted the values for G, the mass of the star, and the delta T. For the computation model, for the part 1, I first calculated the initial and final velocity of the star, and then using the formula P is equal to mv, we calculate the initial and the final momentum. Then we use the formula dp dt is equal to delta P by delta T, which is the change in momentum upon change in time, to calculate the net force. Now we use the parallel component of the net force formula to calculate the net force, which is parallel to the direction of the motion, which is dp dt underscore PAR. Now we use the formula dp dt perpendicular is equal to dp dt minus dp dt parallel. This way we can calculate the net force in the perpendicular direction. Now finally we rearrange the gravitational force formula to find the mass of the black hole, since you know the net force. Now the results are as follows. The fnet came out, the values for fnet parallel, and fnet perpendicular came out to be the following. And the mass of the black hole was found by averaging all the values generated by the simulations, which was 8.82 into 10 to the power 33 kilograms. For the coding part 2, the initial conditions are as follows. The mass of the black hole is the one we found in part 1, and the rest is the same. The speed, the velocity of the ship is the one found through trial and error. So the gravitational formulas were used as discussed before to calculate the net force on the ship and the planet, and then afterwards the velocity update and position update formulas were used in lines 113 till 118 to calculate the velocity and the position of both the ship and the planet at each iteration step. These are the formulas. So the results for part 2 coding. So as you can see, after 60 minutes, the spaceship has effectively escaped the planet black hole system, and the velocity required for this was as follows. So the conclusion questions, what does it mean? So since the rate of the change of momentum is equal to the net force according to Newton's second law, parallel and perpendicular components of the net force are not different from the rate of change of momentum and its parallel and perpendicular components. They're the same thing. The conclusion question, what if? Now, in order to get an orbit for the spaceship, I increased the magnitude of the y component and reduced the magnitude of the x component, and this the following velocity gave me an orbit, some kind of orbit around the black hole. since this is only a coding lab, there weren't any sources of error. Thank you.